All right, let's finish off our discussion here about map projections. Clear the way. Finish off these considerations. So it's a lot like the rules of thermodynamics. You can't win. When we're going from a three-dimensional sphere or ellipsoid or whatever to a two-dimensional piece of paper or computer screen, distortion will happen. You have to give up something to keep other components. Try peeling an orange sometime. Draw the world on an orange and then try peeling it and see what you keep, what you lose when you do that. Because at the core, the three-dimensional shape, the globe, preserves area, shape, distance, and direction. All of those things are true. All of those things are accurate. So, on a map, we can be equal area, we can be conformal, we can be equidistant, we can be azimuthal, but we have to choose one. Azimuthal gets a little bit, you can stack azimuthal with something else in limited cases, but you have to choose one. The globe is everything. What do you want your map to be? Well, these classes of maps preserve some of these globe aspects while distorting the other ones, and making that decision is part of the art and function of cartography. And therefore, part of that is the art and function of doing GIS. It is less of a problem on smaller areas, and it is more of a problem in bigger ones. When trying to map the whole Earth, these issues show up all the time. When trying to map smaller areas, it might not matter as much. But again, that too is the art and science of mapping GIS and cartography. Everything is interrelated. So, equal area maps. Well, one of these isn't an equal area map. Can you guess which one? Well, if you watched that clip at the end of the last video, you know it's not the Mercator projection by Mercator. Actually, if we bring it back real quick, we can see how it is distorting area. Greenland, Siberia, Canada, Alaska, Antarctica, everything at the poles is huge. Distorted. Greenland is not the size of Africa. Africa is a lot bigger. Equal area maps preserve area. The mall wide, the Berman cylindrical here. At the expense of other things. Conformal maps preserve shape. Conformal maps are great for navigation, preserving local angles. Your areas will be distorted, and you'll actually go further. Distance is wrong, but you'll get there. Mercator is conformal. Then we have equidistant maps. Equidistant maps are designed so that the distance along designated great circles are true, or the distance from one point to all others are true. A great circle is just any line that cuts the Earth into two equal halves. The equator is a great circle, as is every line of longitude. We can see a little preview of azimuthal there. Azimuthal maps show true direction from one point to all others, and you can see that azimuthal maps you can set up to be stacked. So you can have an azimuthal equidistant or an azimuthal equal area, just depends on how you want to structure your information. But your navigation is then from one central point to all others. Now, you don't actually have to choose one. You can choose to make everything wrong. Interrupted projections are a great way to do this. Interrupted projections say, Well, we're already cutting the Earth in one spot to make a flat map. What if we cut it in many spots? And this interrupted projection, this one at least, is very much showing the oceans with less distortion. We've got the carvings down the middle of Central Asia, the middle of Eastern Australia, the middle of South America, the middle of North America. So I wouldn't trust this if I was trying to take a road trip. But it is kind of nice to see the equator all interconnected like this. Maybe this is a good storm map or a good tropical weather map. Same thing happens to rafts. No matter what you try to project, you're going to have distortion. And this kind of actually brings up an interesting question, because the map that maybe we are the most familiar with, digitally at least, isn't ArcGIS most likely. It's probably like Google Maps or OpenStreetMap. Bing, I don't know if anyone uses that. But all of these systems, here's OpenStreetMap, are based on Web Mercator. Take the Mercator and put it in your computer and you get Web Mercator. There's an open question for you to think about and consider for a bit. Why would we use Mercator projection, which we know to be distortive, problematic, contains deep issues, at least in interpreting the size of various continents and land masses? So why is it the basis of OpenStreetMap, of Google Maps, all these other things? Think about that for a bit. We'll finish up. No, you can simulate three-dimensional projections with an orthographic projection. So here we're faking it. Works out okay. The dots are not, the globe is not sick here. These are Tissot's ellipses. Tissot's ellipses are great to understand projection changes when you don't want to look at land masses, or maybe you're not familiar with land masses. Not everyone stares at Greenland all the time. I understand that. So the Tissot's ellipses here on this simulated 3D projection are all round. Well, if we move them to different types of projections, we can see that conformal circles are all the same size or all the same shape. Equidistance circles are all the same distance from each other, and equal area circles are all the same area. Some of them get really squished though. So there's another way of thinking about projections. There are over 6,000 coordinate systems inside of ArcGIS, and you can define your own. There are probably more than that in plenty of other places in the world, other GIS systems. When it comes down to it, you just have to remember that the three-dimensional Earth translated to a two-dimensional flat sheet of paper has distortions. It has issues. It has problems. You can't fix them, but you can understand them. That's a good lesson for GIS in general. Well, you might not always be able to fix it, but at least you can understand why it's going wrong.